Hi, I'm Professor Marianne Barber. This lesson is titled Getting Information from the Graph of a Function. Many properties of a function are more easily obtained from a graph than from the rule that describes the function. In this lesson, we will use the graph to determine some of those properties. Upon successful completion of this lesson, you will be able to 1. Determine values from the graph of a function, including domain and range. 2. Compare function values by graphically solving equations and inequalities. 3. Determine intervals where a function is increasing, decreasing, and 4. Determine local maximum and minimum values of a function. 1. Domain and range. The domain and range of a function y equals f of x can be obtained from a graph of f. The domain is the set of all x values for which f is defined, and the range, or the set of images, is the corresponding y values. We'll apply these new definitions to the graph provided. The graph is in the first quadrant. The window of display is 0 to 10 in 2-unit increments on the x-axis and 0 to 8 in 2-unit increments on the y-axis. It is a portion of a downward-facing parabola. Let's draw a solid dot at the left end of the graph to indicate that the point is included, and a circle or an open dot at the right end of the graph to indicate that the point is not included. The domain is the full expanse of the graph on the x-axis. Using interval notation, the domain is bracket because of the solid dot, which means 2 is included to 8, and then open parentheses because of the open dot, which means that the 8 is not included. The range is the full expanse of the graph on the y-axis. Using interval notation, the range is bracket. Again, because of the solid dot, the value looks like 2.4 to 6, and bracket again because 6 is included. 2. Definition of increasing and decreasing intervals of a function. F is increasing on an interval I if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2 in that interval. F is decreasing on an interval I if f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2 in that interval. Consider the graph. The graph is smooth and continuous. The arrows on each end indicate that the graph continues indefinitely toward positive infinity on the left and towards negative infinity on the right. We read graphs from left to right just as in standard English composition. Visually, a graph is increasing on an interval if within the interval the function gets larger. In this graph, the f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2 occurs between x equals -1 and x equals 1. The interval where the function is increasing is open parentheses -1, comma 1, close parentheses. The graph is decreasing when within an interval the function value continually gets smaller. The f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2 in the interval, occurs from negative infinity to -1, and again denoted union from 1 to positive infinity. 3. Definition of local maximum and local minimum. 1. The function value f of a is a local maximum value of f if f of a is equal to or greater than f of x, where x is near a. This means that f of a is equal to or greater than f of x for all x in some open interval containing the value a. We say that f has a local maximum at x equals a. 2. The function value f of a is a local minimum value of f if f of a is equal to or less than f of x when x is near a. This means that f of a is equal to or less than f of x for all x in some open interval containing the value a. We say that f has a local minimum at x equals a. A local max is the highest point on a small interval. Think of riding on a roller coaster. You are at a local max if the only direction possible from that point is down in either direction. When expressed as an ordered pair, we say the max occurs at x equals 1 and has the value of 2. A local min is the lowest point on a small interval. Back to the roller coaster analogy, you are at a local min if the only direction possible from that point is up in either direction. We say the min occurs at x equals -1 and has the value of -2. Exercise 1. The graph of a function f is given. Use the graph to determine. This graph spans all 4 quadrants and has 3 turning points. It begins in the second quadrant with an open dot, decreases to a turning point in the third quadrant, and then increases intersecting the y-axis at 2 as it continues to increase until the second turning point in the first quadrant. It decreases for approximately 2.5 units along the horizontal, turns, and then increases indefinitely. A. The domain and range. The domain is the horizontal expanse of the displayed graph. The leftmost point of the graph is at -5 with an open dot. The open dot means the point is not included. The interval notation is parenthesis -5. The rightmost displayed point of the graph has an arrow which indicates that the graph continues indefinitely to the right. The notation is infinity, and infinity is not a real number and cannot be reached, so we write the parentheses to indicate that fact. The range is the vertical expanse of the displayed graph. The lowest point of the graph is about -5.2, and it is included. So I'll use the bracket. The arrow at the rightmost displayed point indicates that the graph continues upwards indefinitely, so we will denote that with infinity, and close the interval with the open parentheses. Again, infinity cannot be reached, so it's not included. Part B, the intervals where the function is increasing. The graph travels upwards as it traverses from x equals about -3.3 to x equals about 1.1. And we'll denote that with a union symbol. Increases again as it traverses from x equals about 3.7 to the arrow indicates that the graph continues indefinitely as x increases, so we'll write infinity. Close it. A function is neither increasing nor decreasing at their endpoints, so we use the parentheses. C. The intervals where the function is decreasing. The graph travels downwards on 2 disjoint intervals. As it traverses from x equals about -5.1 to x equals about -3.3. Again, we'll denote it with the open parentheses, and we'll use the union symbol, and it again does it from about x equals 1.1 to x equals about 3.7. The endpoints are not included, again, as the graph is neither increasing nor decreasing at these points. D. All local minimum function values and the value of x at which it occurs. The graph has two local minimum function values. They are the turning points in quadrant 3, and the ordered pair is negative 3.3, negative 5.1. The min occurs at x equals negative 3.3. The minimum value is negative 5.1. Notice that at refers to the x values. The value itself is the y value. And the second turning point in quadrant 1, that ordered pair is 3.7, 1.6. Again, the min occurs at the location of x, which would be 3.7, and the minimum function value is 1.6. E. All local maximum function values and the value of x at which it occurs. The one local maximum value is the turning point in the first quadrant. The ordered pair looks like it's about 1.1 for the x, the corresponding y value is 3. The maximum occurs at the x value of 1.1, and the maximum function value is the y value of 3. Solve the inequality x squared is equal to or less than 2 minus x. We'll define functions f and g that correspond to the left-hand side and the right-hand side of this inequality. Let's let f of x equal x squared and g of x equal the line 2 minus x. Now we'll sketch each of the functions. F of x first. I'll complete a t-chart of x values around the origin. I'll label the first column x and the second f of x, and I'll select for the x values negative 2, negative 1, 0, 1, and 2, and evaluate each in the x squared function. So for x equals negative 2, that squared is 4. For x equals negative 1, that squared is 1. At x equals 0, the corresponding function value is 0. At x equals 1, that squared is just 1. And for x equals 2, 2 squared is 4. Let's plot these ordered pairs. So we'll plot negative 2, 4. We'll plot negative 1, 1. We'll plot the origin, which is the 0, 0. Then 1, 1. And finally 2, 4. We know the basic shape of the square function, so we'll connect these points to confirm the shape. And so now we have our parabola with the vertex at the origin. Now we'll complete a t-chart for the line function g of x as well. The first column is labeled x, and the second is g of x. I will select the same x values as for the previous function. So I'll have negative 2, negative 1, 0, 1, and 2 for the x choices, and evaluate each in the linear function 2 minus x. At x equals negative 2, the output, let's see, 2 minus negative 2, which is 4. At x equals negative 1, the output is 2 minus negative 1, which is 3. At x equals 0, the output is just 2. At x equals 1, the function value is 2 minus 1, which is 1. And finally, at x equals 2, that's 2 minus 2, and that is 0. Before we plot all of these points of the line, let's observe that at x equals negative 2 and also at x equals 1, the squared function and the 2 minus x linear function have the same output values. That is, negative 2 comma 4 and 1 comma 1 are intersection points of these two functions. And because we only need 2 points to determine a line, we'll just graph the line using the intersection points. Now we'll connect to get our graph. And now we have a graph that has both the parabola and the line and the intersection points clearly marked. Now we are ready to solve the inequality, which was x squared is equal to or less than 2 minus x. And we'll do that using these graphs. Now from this graph, we observe that the graph of the squared function is less than or below the graph of the linear function between x equals, let's see, negative 2 to about x equals 1. The inequality notation is less than or equal to, so we'll use brackets. The answer in interval notation is bracket negative 2, comma 1, and we'll close with bracket. To ensure understanding, let's solve the inequality when the direction of the inequality is switched. That is, let's solve for x squared is equal to or greater than 2 minus x. From the graph, we observe that the graph of the squared function is greater than or above the graph of the linear function. First, from negative infinity all the way to negative 2, we'll include the negative 2, and so we use the union notation, again from 1, which we include all the way to positive infinity.